Hello, this is Tish Nichols, and this video is the first video in the series on waves, focusing specifically on the idea of conservation of energy. So since this is probably the first video of the year that you're going to be seeing, I'm actually going to open with the most important equation in physics. It's a good place to start. This equation is known as the work energy theorem, and it's powerful because it's incredibly versatile. You can use it in all of the units that we're going to cover over the course of the year, and you can use it in chemistry and biology and all sorts of places. So this single equation is probably where most physicists will start on almost any problem they're going to solve. So hopefully you'll get really familiar with it as the year goes on. For being a powerful equation, you'd think it's very complicated, and maybe it does look more complicated than ones you've seen before. But don't be fooled. It's actually a relatively straightforward equation. All those equal signs basically mean you can equate any two terms in that. So you can make an equation out of two of those four. They're all equal to each other. And a lot of those variables are actually ones that you've learned before in physics, or words that you've learned and probably understand the meaning of. The first two portions of this define a new variable, and that variable is W, or work. Work is a little bit tricky to teach because you guys use that word in your lives, but in physics it has a very specific meaning. In physics, work is defined as the change in energy of an object or a system. So when you learned about energy in the first place, you probably know that objects' energy increases, decreases all the time. Every time that energy is changing, in physics, we'll say work is being done. So anytime energy is transformed from one type of energy to another, or being transferred from one object or system into another, work is happening. So W equals delta E. The second half of this equation tells us how work is done, or how energy is transformed or transferred from one system to another. Um, and the answer is through forces, right? That's where you see those F. And F can be any force, or it can be the net force, depending on whether you're interested in the work done by an individual force or the overall work done by a system. Um, but the F with those little parallel signs and D says that work is equal to the force in a parallel or anti-parallel direction to the distance that an object moves. So work only happens when objects are moving, and the amount of work will always be equal to the amount of force being pushed on the object and how far that object moves. Work is a scalar quantity, which means that it doesn't have a direction. You don't have to say work in the north or south or east or west direction, but it can be positive or negative, and it's really important that you pay attention to those signs when you do your calculations. If work is positive, we say the energy of the system is increasing. So if you think about a ball rolling down a hill and it gets faster, right? We would say that is positive work on the ball because its energy is increasing. Negative work, of course, will decrease the energy of a system or object. So when the ball rolls to a stop at the bottom of the hill, then the object's work is going to be negative because its energy is decreasing. It's important to remember that since energy overall in the universe is conserved, every time there is a positive work, there's going to be an equal amount of negative work on some other object or some other system in the universe so that the overall energy in the universe is conserved. The last chunk of that equation with the cosine, I don't really want you to worry about it too much. It basically applies to forces that are acting in a direction that's not parallel or anti-parallel. If the force is at an angle, that equation allows me to calculate just the portion of the force that's in the same direction as the displacement. So how does this apply to waves? Well, waves are energy. So obviously any equation related to energy is going to be relevant to waves. Specifically, waves are energy moving through space. If you imagine a medium like water, remember that medium means the material a wave is going to be in, and that medium is at equilibrium, which we will define as its lowest energy state, so sort of a flat glass of water. Um, you can add energy to that system of water by exerting a force on it. Obviously, a cannonball is a great example of force displacing the medium or pushing that medium a distance. So the medium has to move and a force has to be present in order to have work. And work is a change in energy. So now that medium has energy in it. That wave energy is going to be moving through the medium in a wave. All kinds of waves are relevant to this equation and to this concept. In terms of conservation of energy, um, we would say that the wave source is the adding energy to the medium, so that would be the source of positive work. And then waves generally dissipate that energy or lose that energy as they move, and that would be the negative work. That negative work can happen in a variety of different ways. They could exert forces on external objects, so we can use waves to push things. But waves also can kind of naturally dissipate their energy um, by a process known as damping, which is primarily caused by internal friction or rubbing between the material molecules as the wave moves. So that wave energy negative work happens in a variety of different ways. Amplitude is the name of the variable that will indicate how much energy is stored up in a single wave pulse. I have a picture of two different types of waves. The top picture depicts a transverse wave that kind of jiggles up and down, sort of what you would think of as a standard wave. And in this wave, the wave pulses are known as crests and troughs. Crests go above equilibrium and troughs go below. In a transverse wave like this, the amplitude of the wave would be measured just in the distance from the top of the crest to the equilibrium or to the bottom of the trough. So usually the units for transverse waves will be meters or centimeters. At the bottom, we see a longitudinal wave, sometimes called a pressure wave. This is standard for sound and a few other types of common waves as well. In longitudinal waves, the pressure pulses are known as compressions and rarefactions. Compressions are the high pressure zones with lots of the medium, and rarefactions are where the medium is stretched out beyond its typical equilibrium spacing. The amplitude in a longitudinal wave, the units kind of depend on the kind of wave, but for sound, you may have heard of decibels. That's a measurement of the amount of pressure stored in a wave compression for sound. It should be pretty clear for both of these waves that the top picture indicates a low energy wave and the bottom picture indicates a higher energy wave. Those bottom pictures were obviously caused by a greater force or a greater displacement of the medium, which means more work went into creating the waves, and that means those waves also have more amplitude. The next couple of slides are going to talk about some wave phenomenon that are tied to conservation of energy. And the first one is what happens when a wave is crossing the boundary from one medium to another. So this can happen all the time, right? Just the sound waves that are coming out of your mouth are hitting all sorts of different media in the world around us, and they can go through those media. We know we can hear sound through solids and through different liquids. So every time any kind of wave, sound or light or anything, hits the boundary of one medium and goes into another, we have a bit of a conservation of energy situation to address because something interesting happens. The energy of the wave actually splits when it hits that boundary. Some of the energy from the original or incident wave is transmitted into the new medium, and some of that energy is actually bounced back into the original medium. This is why you can hear echoes off of walls and see your reflection in a piece of glass. While at the same time, you can also see the things on the other side of the glass because that wave energy actually splits when it hits that boundary. You should, of course, note that in both of these cases, the incident wave has more energy than the split pieces of the wave, and that's due to conservation of energy, right? So we take a big wave and we divide it into two smaller pieces. That way we don't violate conservation of energy. There is something really interesting that happens when waves hit boundaries, and it has to do with the orientation of the waves. Transmitted waves, waves that go through a boundary, are always going to keep the orientation of the pulse that was coming in. So you'll notice in both of those diagrams, we have a crest or an up pulse coming in, and the transmitted waves are also up. However, the reflected portion of the wave is sometimes reflected upright or in the same orientation, and it's sometimes reflected inverted or upside down. That is also sometimes described as a phase shift of 180 degrees, right? Kind of flip-flopping its orientation. And what determines whether the reflected wave is upright or inverted is the relative speed of the waves in the medium, or the relative density of the medium as it moves from one to the other. So when you hit a boundary that is tight or fixed or slow, then the reflected pulse will be inverted. And when you hit a boundary in which the material is faster or looser, then the reflected wave is actually going to be upright. This phenomenon is really important, it turns out, in understanding a lot of the observable properties of light and sound as they hit reflections, they hit boundaries between different medium. The second important phenomenon that I want to mention that has to do with conservation of energy in waves is known as wave interference. Wave interference happens when you have two waves that are both in the same medium and they happen to end up at the same time in the same place. When those two waves pulses overlap, we say they interfere with each other and create a resultant wave. And the amplitude of the resultant wave is just going to be the sum of the individual amplitudes of the incoming waves. This should make sense from a conservation of energy perspective, right? We have the total energy in that system of the rope needs to be conserved. So when the wave pulses hit each other, we have to still have the same total amount of energy. Those wave pulses don't stop, they don't bounce off, they actually will pass through each other. And so as you can see in the picture shown below, that's sort of like time stamps of a wave. Um, those waves overlap, interfere, and then continue on through each other. This first kind of interference shown in this picture is known as constructive interference, and we use that whenever two smaller pulses combine to create a larger pulse in the medium. We also sometimes describe interference as destructive, and in destructive interference, the two wave pulses have opposite phases or opposite orientations. As they meet in the medium, it actually creates a temporarily smaller wave pulse in the medium, and that looks like we've destroyed the wave, and that's why it's called destructive. Turns out we've not actually destroyed any of the energy in the wave. Those wave pulses will regenerate in their original sizes and continue passing through each other after the interference. But this particular phenomenon is also really important when it comes to some of the things we observe when we have multiple waves or multiple wave sources in a single medium. Okay, we've reached the end of the first slideshow. I hope you all think a little bit about how to process your notes best and how to capture sort of the most important parts of this note section, whether it's going back and highlighting things or whether it is jotting down questions. Really, everybody should be able to come up with one or two questions. You don't have to ask them all. They could be points of clarification, but questions also can be points of extension, things that you imagine, might be relevant to this, something you've observed in your life that might be relevant. So, it's been shown by a lot of research that the processing of notes at least once after you take them is really the key to understanding them. It saves you a lot of time when you have to go back and recall this information down the road. So take a few minutes, process however you see fit, and I recommend trying to come up with at least one question that proves that you're sort of thinking about the material deeply. Thanks for watching.